This next example is an interesting one. And at the get-go, we notice that the angle is 3x in each of the trig functions. And so although x is between 0 and 2 pi, we can see right away that 3x is going to be between 6 pi and 0. And this is something we're going to need to keep in mind as we solve this equation. The other thing that's interesting here, and this goes to recognizing identities, and I guess you could say patterns, but tangent and secant are related. The Pythagorean trig identity can be reworked to show that tangent squared x is equal to secant squared x minus 1. And this is going to come in handy in this particular problem. So, strangely, because of this identity, we want to know what tangent squared 3x is. So we're going to isolate tangent as a start, and we'll get tangent of 3x is equal to 2 minus secant of 3x. Then we're going to square each side, and we'll get tangent squared 3x is equal to 4 minus 4 secant of 3x and plus secant squared of 3x. At this point, we're going to rearrange so it looks a little more familiar. Secant squared 3x, like that. And we've got this 4, and we've got this minus 4 secant of 3x. And you may have noticed that I've done something unusual here. I left a little space right here. We'll come back to that in just a moment. Well, I left a little space there because we're going to create secant squared x minus 1, but it's going to be secant squared 3x minus 1. So I've just taken 1 from the right side of the equation, and to undo that, I'm going to add 1 here, like that. And the result of this is the following. This expression is the same value, same quantity as tangent squared 3x. So we can subtract tangent squared 3x from each side. And when we do that, these guys will go away, leave us with 0 equals, and now 1 plus 4 plus 1 is 5, minus 4 secant squared, squared. I left out the squared. Excuse me, no I didn't. Secant 3x, like that. There's a 3x there. When we rearrange this, we'll get 4 secant of 3x is equal to 5. Or secant of 3x is equal to 5/4. And because secant is 1 over cosine, this means that cosine of 3x, which is the inverse of secant of 3x, is equal to 4/5. And this is a number for cosine that's not on the unit circle, so we don't recognize its exact angular value. That is for x. So we're going to take the arc cosine of each side, which yields 3x is equal to the inverse or arc cosine of 4/5. Now with the calculator, we can determine the following, that 3x can be equal to 0.6435. It's quadrant 1 angle. And let's see if we can figure out some of the others. We're going to try to do this without graphing so that we remember how to use reference angles. So I'm going to just draw a little grid here. Quadrant 1. 0.6435 is an angle that's in the first quadrant again. It goes like that, and we can consider that angle like it's a reference angle. And so cosine is also positive, excuse me, over in the fourth quadrant. And so to get to that other angle, we need to basically take 2 pi and subtract 0.6435, that approximation, and we get our second angle right over here. And that angle turns out to be about 5.63975. I'm sorry, not 5, just 6397. Now both of those are between 0 and 2 pi, but this is for 3x, remember, and 3x is between 0 and 6 pi. So we need to find 4 more angles. And to get the 4 other angles, what we're going to do is we're going to find a coterminal angle for that 0.6435. We're going to find a second coterminal angle for that one. Then we'll do the same for the 5.6397. Find 4 more angles this way. And those 4 angles turn out to be the following: 6.9267, 11.9229, 13.2099, and 18.2061. And those angles are all between 0. This is less than 0. That's greater than 0, less than 2 pi. And of course, our last angle here, 6th possible answer for 3x, is also less than 2 pi. Now, at this point, we need to determine which angles are the solutions, because we squared both sides of the equation earlier, and we may have introduced extraneous solutions. And so we can check that with the calculator, check with the grapher or calculator. And without showing that work, we find that the solution set is the following. Now, to get to the solution set, I'm going to go back up here. I'm going to highlight the angles that worked for 3x for the solution. So one of them was this 0.6435. Another one was this 6.9267, and then the 13.2099 also worked. And so because 3x could be those values, the x values, of course, we had to take a third of all the 3x values, okay? And so it leads to the solution set being the following: 0.2145, 2.3089, and 4.4033. And again, that's set notation, and that problem is done. In our next example, we have a half angle. The sine of 2 sine of x over 2 is equal to 1, and our constraints are what we've had before. And what we're going to do here is we're going to isolate the sine of x over 2 by dividing by 2. And so we see that the sine of x over 2 is equal to 1/2. In this particular example, because the sine of an angle being equal to 1/2 is a well-known angle, we can actually determine from this that the angle x over 2 must be equal to pi over 6. And pi over 6 and pi minus pi over 6 is another possibility, because the sine function is positive in quadrants 1 and 2. And so from this we can see that x is 2 pi over 6 or pi over 3. X could also be 10 pi over 6 or 5 pi over 3. And pi over 3 and 5 pi over 3 are both between 0 and 2 pi. So the solution set is pi over 3, 5 pi over 3. We could confirm that with the graph, as we see here. That again is the graph of sine of x over 2, 2 sine of x over 2 minus 1, and that's why the zeros are the solutions. Now we could also use the graph to solve the inequality when is 2 sine of x over 2 greater than 1? And so since we're graphing 2 sine of x over 2 minus 1, we need to look above the x-axis. And so we're going to go from here all the way over to here. And so we can say that our solution is pi over 3 all the way over to 5 pi over 3. Like that. And we're done. Our final example here involves multiple angles, 3x, 2x, and x over 2. This could be a bit of a problem, but with a calculator it's pretty straightforward. And I put this into Desmos, experimented with the dark screen for the first time. It's pretty cool. And we're going to use the x-intercepts method. And in this case, as we've done before in this lesson, we're going to bring everything over to the left side. And we'll create a function that we graph below, sine of 3x plus cosine of 2x minus cosine of x over 2. And when we go ahead and we graph this, we're going to see that we have some possible answers here. And they're all the x-intercepts. There are 4 x-intercepts. Nope, there's 1, 2, 3, 4. There are 5 x-intercepts. So we can write down our answers. Solution is, let's see, we've got 0. We've got 0.727. We've got 2.228. Excuse me, 288. We've got 3.524. And we've got 4 pi over 3. And we're done.